So hello, welcome to another day of physical science. Today we'll start chapter 10. There's only 12 chapters, so 10, 11, 12. We're approaching the end. General idea though, last one was like kind of the beginning of chemistry. It's officially like atomic physics. It's kind of in between the two. This is straight up chemistry moving forward. We're going to do chemical elements this chapter, then we'll do chemical compound or chemical bonding, then we'll do chemical reactions for the next few chapters. And so yeah, we're going to get into some chemistry. Before we get into it, I am once again slightly moving an office hour. I have too many meetings. My Tuesday office hour is normally 2 to 3:30. I'm going to make it 1:30 to 3. If you plan on meeting at me between 3 and 3:30, let me know. I'll make an appointment, but I just have to shift that because I need to be at a meeting at 3. Also, I'm going to turn on another light because I'm very dark. But other than that, that's the general setup. Let's get into it. So at this point, we are, as I said, doing chemistry. And so it's good to first understand what chemistry is. And what chemistry is the study of how one substance can change to another. And basically it's how, you can take a series of chemicals and turn it into another set of chemicals. And it's all based off the composition of matter and the properties of matter. And everything in chemistry really goes to one basic rule, the law of conservation of mass, which says matter cannot be created nor destroyed. That you cannot make atoms out of nothing, or you cannot make atoms disappear. That everything always has to be the same before and after. And that's really what we're going to get into a lot here, is how we can turn one thing to another. You see, people, when they say like it's made out of chemicals, people think like, weird things made in labs. But everything is by nature a chemical. If I have pure water, that's a chemical. It's hydrogen and oxygen mixed together. Everything is chemicals, and we can view how we can treat those individual pieces. Now, modern chemistry has a whole bunch of parts. There's inorganic chemistry, which is the study of non-carbon based molecules. That is what we are going to cover in the next few chapters. There is organic chemistry, which is the study of carbon-based molecules, which we're going to have some organics show up once or twice, but not really any. We're not going to get into it. There's biochemistry, which is the study of chemistry within living things. Organic chemistry is it's alive what once was alive. Biochemistry is it's still alive. It's part of this creature. And analytical chemistry, which is, hey, what if chemistry was all math? We will actually get into a little bit of analytical chemistry at the end of chapter 12, but only a little bit. Now, I'm going to have to get through a lot of names and definitions that I'm going to be using throughout this class. There's a lot of, I'm going to use a lot of nomenclature, a lot of words that I got to make sure everyone knows what they mean. So there's going to be a lot of me just explaining things throughout this chapter. The first bit is we're going to talk a lot about elements. What an element is, it's a substance made up with the same number of protons. And I forgot I had to pull out my periodic table. What I mean by that is if you have an atom, in any given atom, you will have a certain number of protons and electrons and neutrons. We had talked about this last chapter in detail. Sorry, I'm trying to find my periodic table as I talk. And when we talk about an element, what we mean is that the number of protons is just set. And so in an element, it cannot be broken down into a different element. Once you have an element, that's as base as it gets. That they it's the building block. They can't be broken down further. Not without like a particle accelerator. And anytime you have one of an element, that's an atom. That an atom is just the smallest piece you can have of any given element. Now, each element will be defined by its chemical symbol. Well, chemical symbol is either a one-letter or two-letter thing, just to represent what it stands for. Most of them are based off Latin or Greek words. Some of them still match common, some of them don't. But it's just when I say a symbol to represent each element. So like carbon is C, sulfur is S. Those are kind of obvious ones. If it's one letter, it'll always be capital. Some of the two-letter ones, well, in general, some of them don't necessarily match. Potassium is K. Why is potassium K? I don't actually know off the top of my head. Antimony is SB. That's because the Latin word for antimony is stibium. Tungsten is W. That's because the German word for tungsten is wolfram, and that one over. It is of note, though, that it is always a if it's one letter, you always represent it with a capital letter. If it's two letters, the first one is capital, the second one is lowercase. That is very important. The reason why is each capital letter represents one element. If I put capital C, capital O, that's carbon and oxygen. If I put capital C, lowercase o, that's cobalt, which isn't the same. So make sure for each element you have one capital letter. If it's only one letter, it's capital. If it has two letters, one is capital, the second one is lowercase. So in general, here's some common elements in the symbol. I said a lot of them are obvious. Aluminum is Al, argon is Al, barium is Ba, boron is B, bromine is Bl. A lot of them try to be pretty obvious. Not all of them are. Silver is Ag, sodium is Na, tin is Sn. You don't necessarily have these memorized, but they'll come up a lot, so you might want to start recognizing them. Now, in general, as we covered last chapter, all atom is made up of atoms, and atoms are electrons, neutrons, protons. And the structure is a nucleus with neutrons and protons and electrons orbiting. In an element, when you say how many protons you have, that defines what the element is. So if you know something has 7 protons, that means it's nitrogen. If it has 8 protons, that means it's oxygen. That the number of protons defines the element. Now, in any given atom, the number of electrons will match the number of protons. That the electrons and protons will be the same. That isn't necessarily always true. That can be changed. But once that changes, it's no longer an element. It's officially an ion. We'll come back to ions later on. But for now, know that electrons and protons should be the same. A quick aside, this is just kind of here because it's kind of an interesting point. And I kind of think it's neat. Atoms are actually mostly empty space. That they're a thick nucleus and a cloud of electrons. And since all atoms are mostly empty space, that means all matter is mostly empty space. So you would think like you should be able to like merge things together, like X-Men Kitty Pryde style, because it's mostly empty space. The reason my hands can't go through each other is because there's electrons on the outer edge. Those electrons on the outer edge repel each other with Coulomb force. That's why you can't push things through material. It's not because it's like solid. It's actually solid things are mostly not solid. They're mostly empty space. Everything is mostly empty space. It's just the electrons repel. Okay. Now, when we define an element, we define it by its atomic number. Atomic number is just a way of saying how many protons it got. And it once again defines the element. If you have a periodic table, and we're going to get into the periodic table in more detail later on. We're going to get into the periodic table in more detail later on. I will get there as I get there. But we will be using the periodic table a bit with this chapter. And if you have a periodic table, most of the time, in the upper corner, there'll be a number. Iron has a 26. Manganese has a 25. Let's zoom in even further. Copper has a 29. Zinc has a 30. Cadmium has a 48. That is its atomic number. An atomic number is just a way of saying how many protons. And so if I look at carbon, and I'm going to do this a lot where I just have a box like that, that box is made to just look like this right here. That here, I'll shrink this down. that you can see what's in this box and what's on the screen is basically the same within rounding. That's just so I don't have to fit the entire periodic table each time. But carbon has an atomic number of 6. That means carbon has 6 protons. Also, it means that it has 6 electrons, because you can always assume an atom has the same number of protons and electrons, unless, if once again, it's an ion, which we'll get back to. And so when I tell you what element I have, you can tell me the number of protons, number of electrons. Because if I say, hey, you have sulfur, I could just say, I have sulfur. I can say sulfur has 16 protons, 16 electrons, because that's what's on the periodic table. You will need a periodic table for doing a lot of this work. You can just Google and get one online. I think I also give a link to one in a few spots. This does not tell you how many neutrons. You see, there's something, a thing called an isotope. And isotopes are atoms with the same number of protons and a different number of neutrons. Take, for example, carbon. Carbon can exist in multiple forms. The most common is carbon-12 and carbon-13. Carbon-12 is carbon with 6 protons and 6 neutrons. Carbon-13 is carbon with 6 protons and 7 neutrons. They're both carbon because they both have 6 protons, but they have ever so slightly different properties. There's also carbon-14, which is 6 protons and 8 neutrons. That carbon is carbon, but the number of neutrons can make slight changes. Carbon-12 and carbon-13 are once called isotopes of each other. The reason they're slightly different is because they have different masses. You see, most isotopes are stable. Some are radioactive. Anything with an atomic number greater than 83 always radioactive. Some things less 82 and low have some radioactive isotopes. What radioactive means is that it breaks down. That it says, holy shit, we have too many neutrons. Screw this noise, and it shoots them off. Carbon-14 is a mildly radioactive isotope. That if you have a block of carbon-14, it says, I don't want to be carbon-14, and just launches off neutrons so it's carbon-13 or 12. That's what carbon dating is. All living things have a decent amount of carbon-14, and as things are dead, the longer it's dead, the more carbon-14 disappears. So you can tell how old something is by how much carbon-14 it has. What it is with this is we can define for a given isotope, for a single atom, not for just like a block of carbon, but for one atom, we can define what is called its mass number. And here's the general idea. Protons, and I'm going to go back a few slides. Protons have a mass of 1.673 times 10 to the negative 27. Neutrons have a mass of 1.675 times 10 to the negative 27, which is basically the same. 1.67 10 to the negative 27 for both kilograms. Electrons have a mass of 9.11 times 10 to the negative 31st kilograms. Electrons have a negligible mass. That is 0.0009 times 10 to the negative 27. That the electrons wouldn't add up to 4 more digits in for the protons. And so when we talk about the mass of an atom, we can ignore the electrons. And what we'll do is we will define the mass in a unit called AMU, or atomic mass units. 1 AMU is defined as 1.66 times 10 to the negative 27, which is the mass of a proton, which is about the mass of a neutron. And we would define for any given isotope, for a single isotope, the mass number. The mass number is just the mass in AMU of a atom. And how you find the mass in AMU of an atom is you just say how many protons plus number of neutrons. I said before carbon-12 has 6 protons and 6 neutrons. That means carbon-12 has a mass number of 12. One carbon-12 atom has a mass of 12 AMU. Carbon-13 has a mass number of 13. That's because carbon-13 has a mass of 13 AMU. Any questions though? Now, when you look at the periodic table, you see this number on the bottom of each element. It says carbon is 12.01. That is not the mass number. Mass number, once again, is number of protons plus number of neutrons. That is what is called the atomic mass. And the atomic mass is a weighted average of all existing isotopes. About 99% of carbon is carbon-12. It's actually 98.89 to be more precise. 1% of carbon is carbon-13. It's a little bit less than 1, and carbon-14 is less than 1%. And what it is it's just a weighted average. If you have a block of carbon, let's say you got a diamond. Diamond is pure carbon. You can figure out on average how much one atom weighs. Because if 99% has a mass of 12 and 1% has a mass of 13, when I do that math, I get 12.01. That on average, carbon weighs 12.01 AMU. Because 99% of it weighs 12 AMU and 1% weighs 13 AMU. The atomic mass is the number on the bottom of each thing on the periodic table, and it's just how much an atom weighs on average of all of its isotopes. And so on average, one atom of nitrogen weighs 14.007 AMU. On average, one atom of oxygen weighs about 16 AMU. On average, one atom of phosphorus weighs 30.974 AMU. And that's just accounting for all of the possible isotopes. Any questions? Is this making sense? Okay. So, before I get any further, we need to classify metal. We've already done solid, liquid, gas. This is something different. I'm going to put all metal into two categories, and each category has two subcategories. My categories are pure substance and mixture, where pure substances are made up of elements and compounds, and mixtures are made up of homogeneous mixtures and heterogeneous mixtures. Here's the general idea. A pure substance is anything that can be separated by chemical means only and has a fixed ratio of composition. That when you have a pure substance, only a chemical reaction can split it up. Water is a pure substance. Water has the chemical compound H2O. It's made up of hydrogen and oxygen. But I don't care how good of a filter you have, you'll never separate the two. You can do a chemical reaction to separate the hydrogen and oxygen, but you can't just filter them. Pure substances have two subcategories: elements and compounds. An element is something that cannot be broken down further, and it's all made up of things with the same number of protons. That's what we've been talking about so far. I got a hunk of copper, that's an element. I got a hunk of gold, that's an element. I got a hunk of potassium, that's an element. A compound is something that is made up of multiple elements bonded together and can be broken down further. Salt, like table salt, is NaCl, sodium chloride. It's a mixture of sodium and chlorine. They're bonded together. Water, H2O, is a mixture of hydrogen and oxygen. They're bonded together. A compound is something with a chemical formula, which will come back to chemical formulas, but it cannot be broken down through mechanical means. That if you want to break down a pure substance, you can only break it with a chemical reaction. Okay? A mixture is something that can be filtered. Let's say you get some water and it's not very clean, and you put it through a nice filter, and you filter the water and the gunk. That's because it was a mixture. A mixture is something with no chemical bonds, and they're just things mixed together. These can be separated by different means, whether it's using filters or magnets or just picking out by hands. A salad is a mixture. You can pick out the tomatoes if you don't want them. Mixtures come in two forms: homogeneous and heterogeneous. Now, the prefix homo means same, the prefix hetero means different. Homogeneous means it has a definite and consistent property, that it looks the same. Air is a homogeneous mixture. Air is a mixture of oxygen, carbon dioxide, and nitrogen. And you can't just tell where the oxygen starts and the nitrogen begins. Metal alloys are homogeneous mixtures. That steel is a mixture of various metals put together. They're nice, uniform, and you can't tell. You can't say, oh, here's the one thing, here's the other. Salt water is a homogeneous mixture. You just got salt and water. You can't see where the salt begins and the water ends. A heterogeneous mixture is something with the properties aren't the same. And you can tell where one begins and other ends. If you got to think of like Chex Mix or trail mix, and you're like, there's a peanut, there's a pretzel, that's a heterogeneous mixture. It's not uniform. Questions there? We're going to talk about mixtures a lot more in detail at the end of class Wednesday. For now, let's talk about compounds and elements. And I've already done compounds. So really, well, no, sorry, that's a lie. I've already done elements. But actually, let's go further on elements. We'll go further on elements for a little bit. Now, the discovery of the elements, there's of course a story for. Robert Boyle was the first to define what an element is, which was a substance that cannot be broken down, and he said there was 12 elements. Gold, silver, lead, copper, tin, iron, carbon, sulfur, antimony, arsenic, bismuth, and mercury. It's kind of interesting they didn't even know oxygen existed yet. Over time, more elements have been discovered. As of now, we know of 118 elements, 98 of which occur naturally. The remaining 20 only occur by using a particle accelerator and only exist for a fraction of a second. You guys see the history of people discovering it. So Boyle said 12, Lavoisier said 22, Davies said 45, and so on. Now, let's say you got a block of carbon. If you got a block of carbon, you just have a bunch of carbon elements. They kind of stick together, but there's no chemical bonding between them. It is of note that there are 7 elements that cannot exist on their own. Certain elements, they're too reactive to exist independently. You can never have a hydrogen atom. If you have a hydrogen atom, it says, screw this, I'm getting a friend, and we'll bond to something else. Of note, these 7 elements I'm talking about, and like the hydrogen, if you have tried one hydrogen, it will bond to an oxygen or a nitrogen or a carbon, or worst case, to another hydrogen. If you have a substance of one of these elements, they will always form a compound, even if it's only with themselves. These are called diatomic elements. And these 7, that some people might note because they make a 7 on the periodic table, plus hydrogen, that if I look at the entire periodic table, it's this, right? It makes a 7. Although, it only goes down to iodine. These 2, we don't know if they're diatomic because there's never been enough of them in one spot to find out if they are or not. Plus hydrogen. They always exist as a compound. You can never just have one nitrogen atom. You have a nitrogen compound. Nitrogen compound is N2. It bonds with itself. That N2 just means 2 nitrogen atoms shoved together. And this is true for hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. I've heard before you can remember by have no fear of ice cold beer. I'm not going to make you memorize which ones do this, but it is going to come up from time to time. So just wanted to explain. Now, when you look at these, I say these diatomic, they exist bonded to themselves. So N2 is 2 nitrogens bonded together, which is a good time to talk about what an actual compound is. A compound, as I said before, is multiple atoms of different types or the same type bonded together. And what it is for a compound is we can write the chemical formula. The chemical formula just expresses the atoms of each element in a compound and says how they bond together. Take, for example, water. Water is H2O. What that means is water is 2 hydrogens, 1 oxygen. I know that because H is the symbol for hydrogen, O is the symbol for oxygen. And anything subscripted, it's saying how many of that element. If there is no subscript, it means 1. So H2O means 2 hydrogens, 1 oxygen. Sulfuric acid is H2SO4. That means there's 2 hydrogens, 1 sulfur, 4 oxygens. Of note, some chemical formula will have parentheses. In math, if you have parentheses, it means if you have like an equation with parentheses, it means you multiply everything inside of it. In chemistry of parentheses, it means the same thing. Calcium phosphate is Ca3, open parenthesis, PO4, close parenthesis 2. What that means is calcium phosphate has 3 calciums, and this parentheses means everything inside is multiplied by 2. PO4, close parenthesis 2, means that there's 2 phosphoruses and 8 oxygens, because 1 times 2 is 2, 4 times 2 is 8. That's what you get if you have parentheses. Now, if you get into organics, it can get complicated, but you can eventually add it all up. I'm not going to bother adding this up again, but it's just note it can get nuts. Okay, so yeah, whenever you see chemical formula, that's just saying what that compound is made up of and how many of each element. It is of a note the amount matters. H2O is water. H2O2 is hydrogen peroxide. It's a very different substance. Okay. Now, each element can only bond with other compounds in certain ways. And this will actually help us classify our elements. In 1869, a man named Dmitry Mendeleev, he figured out something and created what was the first periodic table. And what he said is the properties of different elements repeat at regular intervals or repeat periodically. And what he said is this happens anytime you arrange the elements by increasing atomic mass. That if you put every element from the lightest element to the heaviest element and put them in order, we'll have properties repeat. And it was kind of fun because he found holes in his theory and said like, this all works, and then there's like a missing element, and he's just like, every 5th element does this, and it breaks down here. And instead of saying it breaks down here, there must be something wrong, he said, you know what? That means there must be another element here that no one's discovered yet, which was actually correct. He was so sure of his thing that when he found pieces missing, he didn't say, oh, my theory's wrong. He said, nope, there are more elements. And yeah, 100% correct on it. He figured out germanium must exist before it was discovered. And this was his periodic table, where it's just elements in order of mass: hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and so on. And he saw that if you put them in this order, everything in column 1 will bond with oxygen in the form of blank 2O, H2O, Li2O, Na2O, K2O, Cu2O, and so on. Everything in column 2 will do a 1-to-1 ratio with oxygen, BeO, MgO, CaO, and so on. And all the way across. These EKA ones were ones that people didn't know existed at the time, but he said had to have existed for this to work. And what year did I say this was? 1869? And that was kind of used for a little while. 45-ish years later, though, someone revisited this idea. And a man named H.G.J. Moseley in 1913 said, wait, it's not atomic mass. You see, at this point, we understood the atom better. Now we had some of the early models of the atom, and we knew protons existed. And H.G.J. Moseley said, you do not arrange them by atomic mass, you arrange them by atomic number, how many protons they have. And he really brought about periodic law. And this is what we believe today. properties of elements, and almost all properties, like most everything about them, reoccur in repeating patterns when arranged in order of atomic number. And trends exist with very few exceptions. And the trends are actually rather obvious in this order. And he created the periodic table of elements. And so what the periodic table of elements is just a list of all the elements in order of atomic mass: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And what they found is that there's patterns for all the properties. And if you have a periodic table in front of you, you can assume some of the properties of a various element just by seeing where it is on the table. Now, periodic table would normally show for each element in the upper left the atomic number, which is the number of protons, the symbol, just to represent it, the atomic mass, which will be an AMU, and the name of the element. Okay. It is of note, you will need a periodic table for the homework. You will need it for the final. On the final, this is kind of an old slide. This is what I would have given you in an in-person final, just like this. Um, for you guys on the final, there will be a page at the beginning with all of the given values and this periodic table. Or at least, I don't know if it's this one or if I give a link to one. I forget exactly how I did it. But there will be a periodic table linked in the final. I've also posted this periodic table on Vanco Hall. So if you needed a periodic table for the homework, you can just go to Vanco Hall. Or as I said, you can just Google them. Okay. Now, everything in the periodic table, we're going to use, more nomenclature, more words to say what things mean to discuss it. But from the very few people who are watching class live, is any questions so far? I'll state that if you're one of the people watching the video and not watching it live, and you do have a question, just shoot me an email. I'll happily go back over the lectures if I miss something that you need to know, since some of you are watching the videos. Although according to my YouTube views, most people aren't watching anything, and that's having some interesting effects on grades, but that's another story. Okay. When you look at the periodic table, we would define what is called groups, also known as families. Groups or families are just vertical columns that I can say this is one group, this is another group, this is another group, this is another group, this is another group, and so on. It's just the names of the columns. All elements in a group usually have the same chemical properties. This goes back to the first periodic table. They all bond with oxygen the same way. That's still true. And that most elements in the same group will react chemically exactly the same, with some exceptions. So like beryllium, magnesium, calcium, strontium, barium, and radium will always react with oxygen the same way. They'll also all react with nitrogen the same way. They will also all react with fluorine the same way, making them kind of predictable. We normally vote a group either by number or by number in a letter. If you look, most periodic tables have at the top just straight up numbering. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we can, but normally they're referred to by letter or number 8 combo. 1A, 2A, 3B, 4B, up here is 3A, 4A. That's just how we define them. A horizontal row we call a period. Why is this not? Oh, because I'm doing that. A horizontal row we call a period. And it's worth noting we number the periods from the top. This is period 1. This is period 2. This is period 3. This is period 4. So like chromium right here, there's nothing above it, but it's still in period 4 because it's 4 rows down from the top. Okay. Now, when we talk about the periods are not as important. We're not talking about the periods as much. But let's talk about the groups or families. We can break the families into a few little subcategories. The first of which is the representative elements. The representative elements are any family with an A in the name. 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. The representative elements are the nice and easy ones. These are your friends. These always react predictably and always follow periodic law and are nice, simple, and always do what you want them to do. We're going to mostly with representative elements because, yeah, it follows the rules of chemistry, always, without an issue. Anything in a B column is what is called a transition element. Transition elements are not so simple. They don't always react the same. In fact, not only do they not always react the same within the family, they don't always react the same with themselves. Iron and oxygen can sometimes be FeO, sometimes be Fe2O3, which is called iron 2 oxide and iron 3 oxide. We'll come back to that. Transition elements are a pain to deal with. We won't deal with them as much. Okay. Then there's the ones on the bottom. Really, whenever you see a drawing of the periodic table, it's not actually drawn necessarily 100% the way it should be. The periodic table, what it should look like is this. Where it's, where it's super wide and has this long spot of 2 in the middle. Thing is, that's kind of a pain to fit on the piece of paper. So normally what people do is they take this section here and they cut it out of the periodic table and jam it on the bottom. Like all of these should exist in this region right here, spreading it out. Those 2 rows you see on the bottom of the periodic table, they are both combined. I only highlighted one, but both of them are called inner transition elements. And there was 2 different types of inner transition elements: the lanthide series and the actinide series. The lanthide series, which I highlighted here, are also known as the rare earth elements. It's because they all appear in nature but are rare, except for promethium. Promethium does not exist in nature and should be part of period 6. Because if I count down 1, 2, 3, 4, 5, 6. Beneath them is the actinide series. The actinide series are usually synthetic and they usually have a short lifespan and are all radioactive and are not naturally occurring. And they're part of period 7. Okay. Now, it is of note, I said all the actinides are radioactive. I should probably say what that is. I kind of mentioned it before, but in more detail. I've said before you can't turn one element into another one. That you can't turn lead into gold. That's alchemy. It doesn't really exist. No matter how much you want to go all Full Metal Alchemist on this shit. Actually, Full Metal Alchemist, the show, tries to be really good about the laws of chemistry here. However, radioactivity is another thing. Radioactive materials, like once again, everything in the actinide series, what it is they are unstable. And I said before that they'll just shoot off extra neutrons. But some radioactive things will actually shoot off neutrons and protons. This right here is a piece of, oh, did I not write what it is? Uranium. This right here is a piece of uranium in a cloud chamber. And you can see these streaks forming. That is alpha particles shooting off, where alpha particles are 2 neutrons and 2 protons. What happens with radioactive material is that it just rockets off protons. And when it rockets off protons, it changes the number of protons, it changes what element it is. And so anything in that actinide series, that if you have a piece of uranium, let's go classic, uranium's in that series, uranium won't stay uranium for long. It'll launch off protons till it becomes some other stable element. Now, it is of note the actinides are in all of the radioactive elements. Everything from atomic number 83 and higher is radioactive, plus also technetium and promethium, which is 43 and 61 respectively. Okay. Okay, some of the other metals get some special names that are worth knowing. Column 1A is called the Alkali Metals. Hydrogen is officially not an alkali metal. Most periodic tables put hydrogen in group 1A. You'll find some that don't, and instead they shove hydrogen like right here floating in the air, middle of nowhere. That's because hydrogen's really fucking weird. We'll come back to that as we move forward. But hydrogen is officially not part of group 1A. But the rest of 1A is the alkali metals. They all have the same properties when mixed with other chemicals. And fun fact, they also react explosively with water. Column 2A is called the alkaline earth metals. They all occur freely in nature, and they both also don't really like water. Oops, didn't mean to hit that. That alkali metals and alkaline earth metals both react with water. Alkaline earth metals not as explosively though. None of the transition families have a special name, and 3A, 4A, 5A, and 6A also do not have special names. The only other ones with special names is group 7A. 7A is the halogens. Of note, they're all super toxic, and they can all mix with hydrogen to make an oxygen. And family 8A. 8A is known as the noble gases. They're all unreactive. They will not chemically react with anything else unless you put a shit ton of effort in. And they're sometimes also called the inert gases. Any questions? So, everything in the green circle, they have A in it. Those are representative elements. Anything in this region, I missed. I shouldn't have those two on the bottom. Let's try that again. These are transition elements, and these are inner transition elements. Okay. Another way we can refer to elements is whether they're metallic or non-metallic or something else. Metals are usually solid, lustrous, high melting point, good conductor of heat and electricity. I mean, yeah, they're a metal. They're shiny, you can shape them, and they conduct heat and electricity. They're known to be malleable, they can pound into sheets, and ductile, can be drawn into a wire. Nonmetals have much lower density, have low melting points, and do not conduct heat well or temperature. And you cannot put them in a shape. Most of them don't even exist as a solid at room temperature. They'd be a gas. But those that are a shape that if you try to hit it with a hammer, instead of flattening it, you just crush it into powder. Semi-metals, sometimes called metalloids, are somewhere in between and can have properties somewhere in between. Now, it's going to be really important whether an element is a metal or a non-metal. If I go back to the periodic table I'm giving you on the exam real fast, you can see I put this staircase bit separating off there. That staircase bit, that's the important bit here. That represents the branch between metals and nonmetals. Metals are everything except for hydrogen to the left of that staircase. And nonmetals are everything to the right of that staircase. You see, chemically, how we define a metal and a nonmetal is a metal is anything that likes to give away electrons, and its chemical reactions were based around it giving away electrons. We're going to talk about that in more detail later on. A nonmetal is anything that accepts electrons and doesn't want to give any away, it just wants to take. So metals like to give away electrons, nonmetals like to take electrons. Once again, we'll cover that more in detail later. But really what we can define metals and nonmetals is whether they give or take electrons. And to go further, we can define something's metallic character. Metallic character is how readily something will give away an electron. And something is more metallic means it's more likely to give away an electron. And this follows the periodic trend. Metallic character increases anytime you go down in the periodic table or to the left. Fr in the bottom left corner, francium, is the most metallic element. It is the most willing to give away electrons. Helium in the upper right corner is the least metallic character. It is the least likely to give up electrons. And we can just define anything further to the left is more metallic. Anything further down is more metallic. I can say that iron, well, that's a bad color for that. Iron is more metallic than cobalt. Gold is more metallic than silver. This has to do because the electrons are just further away from the nucleus, and how far away in Coulomb force. We can also define non-metallic character. Non-metallic character is just the inverse of metallic character. Helium is the most non-metallic element. And so I can say cobalt is more non-metallic than iron because it's to the right. Silver is more non-metallic than gold because it's above. It's just the opposite thing. Okay. Questions there? All right. In summary, here you go. Hydrogen is weird. Everything else in 1A is the alkali metals. Everything in 2A is the alkaline earth metals. Everything in the B columns are the transition metals. Metallic, but in the other side of representatives, those are your regular metals. Semi-metals are somewhere in between. Some of the non-metals are these green guys. Family 7A is also non-metals, but they're officially called the halogens. Group 8A is also non-metals, but they're officially called the noble gases. And the lanthide and actinide series are off on the bottom. Of note, we can also define the phase of elements, aka solid, liquid, gas. At room temperature, most things are solids. At room temperature, only two elements are liquids. They're mercury and bromine. It's of note, gallium is close. Gallium becomes a liquid at about 90 degrees Fahrenheit. So if you have a piece of gallium and you put it in your hand, it'll melt in your hand. At room temperature, only 11 elements are gases. It's hydrogen, nitrogen, oxygen, fluorine, chlorine, and the 6 noble gases. It's of note, all those ones that are gases are all those diatomic ones. It's not all the 1, 2, 3, 4, 5. It's not all the diatomic ones because there's also iodine. Is that I think what I'm missing? 2, 3, 4, 5, 6, 7. Yep, I'm missing iodine. And I'm missing something else. Oh, bromine. I'm missing iodine and bromine. But the rest, those are the only ones that are gases at room temperature. The rest is solid at room temperature. You can always make something a solid. My research when I used to do it was we did research at 4 degrees Kelvin. At that temperature, oxygen is not even a liquid; it's a solid, which really sucked. But for the most part, most everything is a solid at room temperature, except for the 2 liquids and the 11 gases. Okay. Also, now you know what? I'm going to stop here because the bit I'm about to get into is going to get into a very complicated topic that I cannot finish in 2 minutes. So I'm just going to stop there for the day, and we'll pick up on electron configuration on Wednesday. So unless there's any questions, we'll stop there. Okay. Have a good day.